Hi everyone, welcome to my new video. Today we are going to discuss about tokenization techniques, which is an essential step in natural language processing, specifically when you are working with large language models. We'll start with different types of tokenization methods. I'll briefly explain the concepts behind each and we'll try implementing these methods from scratch or by using libraries like NLTK or SPACY. After that, we'll dive into some of the more advanced and widely used tokenization techniques such as WordPiece, Byte-Pair Encoding, Unigram, and sentence piece. Remember, these methods are being used in state-of-the-art language models. Finally, we'll put everything together by building an advanced tokenizer. We'll use custom dataset and implement this with the Hugging Face tokenization library. So let's explore the major tokenization techniques used in NLP systems. Now, tokenization is all about breaking down the text into smaller parts, which is called as tokens, so that the model can understand and work with the smaller things like tokens. Now, why this is important? Well, how we split up the text can greatly impact a model's performance, efficiency, and even its accuracy in generating or understanding the language. Now, this tokenized text can be further processed for tasks like converting all words to lowercase, removing stop words, and stemming or limitations. So, basically, the normalization process. Now, this normalized text is often converted into numerical form, or we say it as a vector form for the machine learning models to understand. Now, common techniques that include to convert this tokenized text to vector form is bag of words, TF-IDF, or word embeddings. We'll discuss all about this maybe in later session, but for now, let's focus on different types of tokenization techniques. If you see on broad level, tokenization is categorized to these 5 types of different tokenization method: basic tokenization method, word and sentence based tokenization method, phrase and expression based tokenization method, custom or rule based tokenization method, and advanced tokenization method. We'll cover each one step by step. So let's start with basic tokenization method. In basic tokenization method, we have white space tokenization, punctuation based, character and number tokenization. Now this white space tokenization split the text based on the spaces. Each word is treated as a token when separated by white space only. It's simple but doesn't handle punctuations or complex language structures well. Now, in case of punctuation based tokenization, text is split not only by spaces but also by punctuation marks. It improves upon the white space tokenization by separating words from the punctuation. The third is character tokenization. Now, it treats each individual character as a token. It's useful in some cases like in languages which is having complex character system. The last one is number tokenization. In case of number tokenization, numbers in the text are treated as separate tokens. This is important when numbers hold special meaning or when you need to analyze numerical data separately from the text data. Now let's look practical implementation of all of these tokenization methods. So in case of white space tokenization, we'll just split the text, and as you can see here, we have the tokens splitted based on the white space only. In case of punctuation tokenization, we'll split the text based on some regex, where in the regex is to find out the sequence of word characters or punctuation characters, which is actually not a word or white space. If you see here, the punctuation is divided or splitted from the word only. Now the next is character tokenizer, where we are just treating each character as a token. And the next is number tokenization. In case of number tokenization, we'll try to find out the sequence of one or more digits or sequence of one or more non-digit characters. As you can see here, the text is divided based on the number. Though these are very simple and easy to implement, but these are very ineffective with noisy data, and they are poor for complex languages. Now we'll discuss the second category of tokenization, which is word and second based tokenization. In this category, we have word, sentence, tree bank word and tweet tokenization. Now, word tokenization split the text into individual words. It handles spaces but sometimes struggles with punctuation or contraction depending on the implementation. So, sentence tokenization breaks the text into sentences. This is helpful when you need to analyze sentences independently. The tree bank word tokenization is designed specifically for more complex cases, like it handles punctuations more intelligently, splitting of common contractions and separating punctuation from the words. It's widely used for tasks like syntactic parsing. Now, tweet tokenization is used for social media text, particularly Twitter. It handles the informal language, which is like hashtag or mentions, which is at the rate, some type of emoji, and URLs that are common in tweets. Now let's implement word and sentence based tokenization methods. We'll be using NLTK library to basically check our uh, Scratch implementation with NLTK implementation as well. Let's say we'll define word tokenization. So for this we'll create a regex to find out all the words. We'll match actually with the entire words. So basically that's why we have included boundary, and then we'll find out all the punctuations also. So either this or the punctuation mark that we are defining. So based on this, just split the text. So if you see here, the text is splitted based on the punctuation as well as white space. So all the words are different, and if you see here, NLTK also is giving the same output. Now let's define the sentence tokenization. In case of sentence tokenization, we are trying to define a regex where we'll basically check the look behind using the look behind function, all the basically a sentence, and then we're trying to find out a I mean to say a punctuation mark and a space character. Either it can be one or it can be more spaces that actually follow the punctuation mark. If you see here, the text is divided based on the punctuation mark and then space. So basically the sentence, and here we are getting the same using NLTK also. The next one is tree bank tokenization. If you see here, as I said, we are replacing, I mean to say, we are doing some type of replacement for contractions. Let's say for NT, we are separating out from the word want. Okay, so W and N T will be different words. So we have defined a regex to find out, I mean to say just to replace that, and we can get the simple tree bank tokenization here. If you see, the word W and T are replaced, I mean to say splitted. Which if you will be using normal word tokenize, it will be part of the same word, and in using NLTK we are getting the same as well. The next one is the tweet tokenizer. If you see here, I have provided a text with @ and hashtag, all those things, and we can create a regex to find out all the words that start with @ or hashtag or having some type of I mean to say normal word, all those things, and then we can find out the we can split based on that only. And if you use the tweet tokenizer from NLTK, we can get the same here as well. Though this tokenization handles grammatical syntax better, but they struggles with contractions and informal text. Now the third one is phrase and expression based tokenization method. These techniques go beyond basic word level tokenization, focusing on meaning and context. Phrase tokenization groups words into phrases that form meaningful units. So instead of splitting each word individually, it recognizes common word combinations or phrases. This is useful when you are working with proper nouns or collocations that frequently appear together. Multi-word expression tokenization is designed to recognize multi-word expressions or group of words that together convey a specific meaning and that cannot be deducted from the individual words alone. Now, this multi-word expression tokenization is essential for handling fixed expressions or some type of technical terms like machine learning. Now, semantic tokenization goes a step further by breaking down text based on the meaning or semantics of the words. So, rather than their structure or appearance, it focuses on the semantics of the words. Now, it attempts to group tokens that represent the same concept or entity. This type of tokenization is useful in tasks like machine translation or information retrieval. Let's implement phrase and expression based tokenization. For phrase tokenization, we'll define a regex to find out any of these punctuation characters, either one or more occurrences. Then we'll try to find out any spaces, either it is 0 or more occurrences, and then we'll split based on that. So if you see here, the phrase hello world is retained as the part of the same token. And the next one is the multi-word expression tokenizer. So if you see here, we have provided a input to treat machine learning and large language models as a part of the same tokenization, and we have just replaced that with a underscore to join these two texts so that it will be a part of the same word or same token. And if you see the output, we are getting the tokens machine learning and large language models as the one token. Now let's implement the semantic tokenizer. In case of semantic tokenization method, so we'll be using spaCy. So here we are trying to create different rules, or we'll create different regex patterns to find out different type of entities. Okay, so what it means is, for example, let's say we are giving a name, that's name of a person that should be identified as a person. If we are giving as a date, that should be identified as a date. So we have created two patterns here, people and date. Then what we are doing is we are trying to iterate on each token and check what type of pattern it falls into. And that's what in case of spaCy also we are getting the same. Okay, and if it is not part of any predefined patterns, then it can be a unknown entity. If you will see here, all the tokens that we are getting is having a information, semantic information, and that then we can group them into different entities based on their entity type. Now let's discuss about the fourth category, which is the custom or rule-based tokenization. We have regex, rule-based, statistical, and n-gram tokenization in this category. Regex uses a regular expression to define specific patterns for splitting the text. This allows for highly customizable tokenization based on the patterns you want to capture. For example, let's say you want to capture the email format or the phone number format. So you can create different type of regex and it will capture all those things and split based on that only. Now rule based tokenization is like same, but here you can define custom rules instead of pattern matching. Statistical tokenization is based on the likelihood of the word boundaries in the text. This is often used for languages where words are not clearly separated by spaces like Chinese or Thai, and algorithms analyze large amount of text to predict the most likely places to split the text into tokens. This approach is useful when simple rule-based tokenization is insufficient due to the complexity of the language. Now the n-gram tokenization split the text into sequence of n consecutive tokens, which is word or characters. This method is commonly used in the text prediction models and machine learning tasks, as it captures word or character patterns and sequences. Now let's try to implement some of the custom tokenization methods. We have almost implemented a lot of regex and rule-based tokenization methods previously, so we won't be implementing more regex based tokenization methods or rule based tokenization methods. So we'll go for n-gram tokenization method. So let's define a n-gram tokenization method. Here we will tokenize the text by splitting its spaces. Then we'll create n-grams from the list of tokens. For example, for the bigram, it will create the pair of consecutive tokens, as you can see here. all of these tokenization methods we have discussed work really well when you have a large and extensive vocabulary. But what happens when there are limitations on the size of the vocabulary? What if we encounter words that are not part of our vocabulary, or we can say this as a out of vocabulary words? In real-time applications, it's common to run into rare and unseen words that actually not covered during training. So how do we handle that also? So we need some type of tokenization techniques that can generalize well, and even when the exact word isn't in our vocabulary, we can still get some type of information from them. This is where advanced subword tokenization methods come into play. These methods allow us to break words down into smaller and more frequent subword units, ensuring that we can still capture some type of meaning. So it means rather than treating out of vocabulary words as a unknown, we can still treat them as a meaningful component. We have syllable tokenization, character engram, WordPiece, Byte-Pair Encoding, Unigram language model, and sentence-based tokenization in this category. Now, syllable tokenization breaks down words into their syllabic components. This method is useful in languages where syllables play a significant role in meaning or pronunciation, and it can also be helpful in speech processing also. Similar to word level n-gram tokenization, character level n-gram tokenization breaks text into sequence of n characters. This method captures the structure of words at the character level, and it is commonly used in tasks like spelling correction, morphological analysis, or when we are dealing with some type of languages where words are made up of smaller character units like Chinese or Japanese. WordPiece tokenization breaks the words into smaller meaningful units or subwords. Let's see the steps involved to build a WordPiece tokenization. The first step is build the vocabulary and then build a tokenizer. So to build the vocabulary, what we will do, we will count the frequency of each word in the corpus that we have provided. Now for each word, we will generate meaningful subwords. So we will be splitting the word into prefix and suffixes. And suffixes will be concatenated with hash hash. And we will add both prefix and suffix to our vocabulary. Now we will sort all these subwords by frequency and keep the top words of our provided vocabulary size. Now in the next step we will do the actual tokenization. What we will do, for each word that we have given as an input, we will search for the longest matching subword in the vocabulary. We will start from the longest subword and we will work backward. If the whole word exists in the vocabulary, keep it as it is. Otherwise, split it into subwords like prefixes and suffixes, the way that we have done in while building the vocabulary. Now we'll repeat the same thing until all the characters are tokenized. If there is no match, then we'll replace the word with unknown token. WordPiece tokenization is majorly being used in models like BERT. Let's see another advanced tokenization technique, which is Byte-Pair Encoding tokenization technique. Now in this, it starts by splitting all the words into individual characters and then iteratively merges the most frequent pairs of the characters or subwords into larger tokens. Let's see what are the steps involved while you are building a Byte-Pair encoding tokenization. Initially, each character is a token in this case, and a special end of word marker is added to distinguish word boundaries. In each iteration, we'll count pair frequencies. So what we try to find here is the most frequent adjacent token pairs. Now we'll merge the most frequent pair and replace it with a new token. Then we'll update the vocabulary and the text, and we'll repeat these three steps until the desired vocabulary size or number of merges. So basically the merge condition, when it is being reached, then we'll stop it. Let's say we have input text banana and banana. The initial vocabulary is this, which is having all the characters of this text. Now in case of step 1, we see that most frequent pair is A and N, okay, with count 4. Then we'll merge this and we'll update the vocabulary with a new subword. In the second step, the most frequent pair is BAN. Then again we'll repeat the same. We'll add these to vocabulary and we'll merge and add these to vocabulary. And finally, we can see here we have the final vocabulary is this, where we have the vocabulary which is based on the merging criteria, and we have the final tokenization test based on the vocabulary word that we have got. This method is very much used in transformer models like GPT. In case of Unigram tokenization, a set of tokens is predefined based on a probabilistic model which estimates the likelihood of different token combinations. Each word is then broken down into most likely combination of tokens from this set. Unlike Byte-Pair Encoding, which merges subwords based on frequency, Unigram tokenization can discard less useful tokens and only keep the most likely ones. Let's see the steps involved while you are designing a Unigram language model tokenization. Let's say we have the initial vocabulary having each token and their probability. For example, I and like here is having initial probability of 0.4 and 0.3. The goal here is to optimize this vocabulary with expectation maximization step. Let's say we have a input text which is I like learning. We can use different tokenization methods and we can get three type of tokenization like this. I like learning a tokenization, I like e-learning is another tokenization, and this is the third tokenization. Now we'll try to find out the probability of each tokenization method. Probability of each tokenization equals to the multiplication of probability of each word in that particular tokenization. Since we are treating each word independently, we can use multiplication to get the total probability. So for example, for I like learning tokenization, the probability equals to 0.4 into 0.3 into 0.2, which is 0.024. For this tokenization method, probability is equal to 0 because like this token or this word is not in our vocabulary. Now for the third tokenization, we have the probability equals to 0.0003 using the same approach. The next step is maximization step. We use the expected counts from the previous step to update the subword probabilities. Subwords that appear more frequently in likely tokenizations will have their probabilities increased. So in this step, we'll try to find out the expected count of a particular word. Expected count of that particular word is a summation of tokenizations containing that particular word, and in that tokenization we'll try to find out the occurrence of that particular word into probability of that particular tokenization, and then we'll sum this for all the tokenization. For example, let's say expected count of word I equals to, for this particular tokenization, I has appeared only once. So occurrence is 1 into probability of the tokenization is 0.9876. So 1 into 0.9876 plus for this tokenization we have the same I appeared once. So the occurrence is 1 into 0.0123. So total is 1. Same way for like it is 1 also. But for learning, if you see here, we have learning in this tokenization, but we don't have that word in this tokenization. So the probability is here like occurrence is 1 into 0.9876. So updated expected count is 0.9876, and same goes for all other words. And finally, if we'll add these all, we'll get the total expected count. And the updated probability is the expected count of that particular word divided by total expected count. And here we can get the updated probability, and then we'll update this in the vocabulary. Now the next tokenization method is sentence based tokenization. Sentence mesh is actually a unsupervised algorithm for subword tokenization. It treats the input text as a continuous stream of characters and applies a language model to tokenize it. Now, the primary idea behind the sentence piece is actually byte-pair encoding or any type of Unigram language model. Now, the goal here is to compress the text, finding common substrings, so frequently occurring character pairs or subword units are merged until a desired vocabulary size is reached. Now, Unigram is not used directly for any of the models in the transformer, but it's used in the conjunction with sentence-based tokenization method. Now let's implement all of these advanced tokenization methods we have discussed so far. The first one is C-level tokenization. So let's define a C-level tokenization method where we'll be using the Python library, which is the predefined library. And if we'll use the method, you can see based on the syllable it is splitted. Now the next one is character n-grams. As we have seen in case of word level n-gram, we have different consecutive words. The same goes to here also, we have consecutive characters instead of words. So for the word given here, if we'll pass to get the trigram, then we'll get the character level trigram here. Now let's build a WordPiece tokenization method. As we have discussed in the previous slide, we have to build a vocabulary and then we have to apply the tokenizer. So the first step is pre-process the text, like converting that to lowercase and removing all the non-alphabetic characters. Then what we'll do, we'll build the vocabulary based on the given text, and then we'll use the WordPiece tokenizer to tokenize the given word. For example, if our input corpus is the affordable car is fantastic and the car is unreachable, affordable cars are great, then we'll be pre-processing and then we'll be building the vocabulary. If you see, in case of vocabulary building, we are splitting the words into prefix and suffix, and then we are adding the subwords to our vocabulary based on the frequency. Then we are calling our tokenizer method to parse our input sentence, tokenize our input sentence. So if you see, in case of tokenized words also, it is trying to check all the prefix and suffix in case the word is not matched in our vocabulary. If you see here, for the input text, the affordable food is unreachable, we are getting some subwords here. Now let's implement the byte-pair encoding tokenization method. For this, we will define a function to calculate the pair frequencies. Then what we will do is we will define a function to merge the most frequent pair, and then finally we will define our BP tokenizer, which will iteratively merge our subwords into our vocabulary and update our vocabulary as well as update our text and their subwords. If you see here, what it tries to do is it initialize the text. So basically, for the starting, each character is a tokenized text, and we have appended a specialized token as we have discussed. And then what we will do is we will try to merge till the time our merging criteria is not. Then what we will try to find out is the most frequent character pair. Okay, and then based on that we will merge the characters and then we will update the vocabulary, and then we will be having the updated tokenized text as well. If you see here, the initial vocabulary was this, then in the first step A and N is merged and this is added to vocabulary because the count was maximum, which is 4. In the second step, B and N is merged with count 2 and vocabulary updated to this, adding this word. Now in third step, AN is merged and the vocabulary is updated to this. The final tokenized text is this and the final vocabulary is this. So we can use the transformers GPT-2 tokenizer to get the same type of tokenization because it used byte-pair encoding. Now let's implement a pre-trained Unigram tokenizer with sentence piece. Actually T5 is one of the model that uses a pre-trained Unigram tokenizer. We can actually load it and to tokenize. If you see here, it's tokenized based on the sentence piece tokenizer. Now let's see how we can build a custom advanced tokenization using Hugging Face tokenizer. To build our own tokenizer for our large language models, these are the steps that need to be followed. First one is normalization, which is actually standardizing the text by cleaning and formatting for consistency. The second is pre-tokenization, so it's basically splitting the text into initial tokens or chunks for processing. The next one is tokenizer or trainer. So what I will do is we will create a tokenizer and a trainer, which is basically some type of predefined class in Hugging Face framework. Sorry, Hugging Face tokenizer framework. Then what we will do is we will load our corpus on which we are trying to build our own tokenizer. Then we will define a post processing method. Then we will defining a post processor. Well, to adjust tokenized outputs with padding or truncation or special tokens. Then we'll implement encoding and decoding method. So to convert between text and token IDs and token IDs back to text. And then next we'll see how we can save this and reload and use that saved tokenizer. Now let's implement our own custom advanced tokenizer. We will be importing the decoders, models, normalizers, all of these components from the tokenizers library. The first step is normalization. So let's create a normalizer method to get the normalizer that we want. For example, if it is BERT, then we can directly get the BERT normalizer. If the normalizer type is sequence, then we can get a sequence normalizer, which can be a sequence of NFT, lowercase and strip accent. So basically lowercase converts all character to lowercase, strip accents removes accents from the characters, and NFT decomposes character into base characters. For example, E will be converted to normal E. Okay, so this is what we can use to create a sequence of normalizers. And if we want to create a, you can say, different sequence where we can replace the left double quote with standard double quote or right double quote with standard right double quote, so all those things. And again we can include NFT or strip accent, or we can use some type of regex to replace, so we can create some type of custom sequence here as well. If you see here, after applying the normalize str function, if you see here, all these text are pre-processed and all these things that is actually not relevant are removed. Now the next step is define a pre-tokenizer. So as we have discussed, we need a pre-tokenizer to just split the initial text. So let's define different type of pre-tokenizer. If it is BERT, we can just load the BERT pre-tokenizer. If it is only white space and punctuation, we can use the white space pre-tokenizer, and if it is only white space, then we can use white space split. And if it is sequence, then we can create a sequence of pre-tokenizers as like the way we did for normalizer. And if it is BP, byte-pair encoding pre-tokenizer, we can use the byte label. And if it is Unigram, then we can use the metaspace pre-tokenizer. And when we apply the same, you can see what we are getting is the splitted token. Now the next step is define a trainer and a tokenizer. So for example, let's define BP tokenizer. So what we can do, we can load the models.bp and we can pass the unknown token that has to be provided for that particular type of tokenizer. Same goes for Unigram. So we can provide unique token as well as some special token if we want to add. For example, here for Unigram we are adding these all special tokens, and same goes for WordPiece as well. So we can use models.wordpiece from the tokenizers library to load the WordPiece tokenizer and corresponding trainer as well. Once we have all these things defined, let's load our dataset, and we'll be using the Wikitext dataset, and we'll be using a subset of that dataset because we want to train it faster. Now what we'll do is we'll try to get the tokenizer and trainer that we have defined. For example, we are getting the Unigram tokenizer. To that tokenizer we will be adding our normalizer and pre-tokenizer, and then we'll call the tokenizer.train function to train the on the Wikitext dataset with our trainer that we have defined. It will take some time. Now here it is being trained. Let's define the post processor here for different type of post processing. So let's say for WordPiece we have to define different post processing. For BP we have to define different. While we define different type of post processor, we have to take care of two things. We have to see what is the token ID, sorry, class token ID and separator token ID for that tokenizer, and then what we will do is we'll pass this token ID to template processing method with our format for single sentence and pair sentence. Now let's check our tokenizer using the encode function. So we'll pass the text to the encode function, and we'll find out all the tokenized strings and list of that token IDs corresponding to that string, and list of segment IDs. So basically if we are passing different sentence, we can get 0 for first sentence, 1 for second sentence, and accordingly. If you see here, we are getting all the tokenized and separator for the first sentence and the separator for the second sentence. Now let's try to define a decoder. In case of decoder, what we will do is we will trying to give the IDs, and then we will get the original text back or original token back. So if you see, when we have provided the encoding IDs, then we are getting the original text or the text that we have provided, okay, or the decoded text. Now let's save the tokenizer that we have trained, and using the tokenizer.from file method, and we'll save this in JSON format. Then what we'll do, we'll use the pretend tokenizer first method from transformer library to reload our tokenizer, and we'll be adding all the special tokens that we have defined, and then we can use this tokenizer as our custom tokenizer. Here is a chart you can refer if you want to use different type of tokenization methods, and in which condition and which scenario which tokenization methods you can use. You can just take a look around. I think that's it for today, and thank you for watching.